Hello everyone, good afternoon here. Also I should say good morning and good night all together. We are starting the English part of the second day. In this session, you have 2 lectures, and after the last one, you will take another group photo. This was requested by our participants. The first speaker is Professor Nick Trefethen. Thanks him for accepting our invitation. I'm asking Dr. Behnam Hashimi to introduce Professor Trefethen. Behnam, please.
Hello everyone. Welcome to this first plenary talk of this second day of the 10th seminar on linear.
Behnam, please open your camera.
It is on. All right.
You should. Yes.
Okay. Can you see me now? Can you see me now?
Yes.
Okay. Our speaker today is Professor Nick Trefethen from the University of Oxford. Nick, of course, does not need any introduction for many of us because he's so well known. But nevertheless, for those of us who don't know him very well, let me say something. So Nick is Professor of Numerical Analysis at the University of Oxford Mathematical Institute. Nick was president of SIAM during 2011-2012. He is a fellow of the Royal Society, a fellow of the American National Science Foundation, and a member of the American National Academy of Engineering. So Nick has won several prizes for his groundbreaking contributions to numerical analysis. I'm going to just mention 2 of Nick's prizes. One is the SIAM John van Neumann Prize for his work across several areas of numerical analysis. And the other prize that Nick has won, and I would like to mention, he has won more prizes, of course. The other prize I would like to mention is SIAM George Polya's Prize for Mathematical Exposition. When it comes to clarity of writing and mathematical exposition, it's very hard to find any other mathematician who can compete with Nick. Nick has written 10 books, and I have four of his books here on my bookshelf that you can see. So the first one I would like to mention is Numerical Linear Algebra, co-authored with David Bow. This is published by SIAM, and this is SIAM's all-time bestseller. So one key aspect of this book is the early introduction of the single value decomposition, which is then used throughout the book. And I myself use this book for my own teaching, and I know that several other professors across the world do the same. Another book by Nick that I would like to that I have is Spectral Methods in MATLAB, which has MATLAB books on many pages. This is also published by SIAM. The third book by Nick that I would like to mention is Spectra and Pseudospectra, the behavior of non-normal matrices and operators. This is co-authored with Mark Embry and published by Princeton University Press. Let me just read something from the first few pages of the book. So in the first few pages of the book, you see a quiz, so a plot and a quiz about two by two matrices. And then if you go to the next few pages, so it says, note to the reader. The style of this book is unusual. There are 60 short sections, and nobody will read them all. And then they say, but please, though you won't read all the words, look at all the figures. You will quickly feel the pleasure we have found in years of exploring spectra and pseudospectra. So I guess this shows how Nick understands mathematics and would like others to understand mathematics. So through looking at carefully at the plots that you get from software. Another book by Nick that I would like to mention, and is close to his talk today also, is Approximation Theory and Approximation Practice. also published by SIAM. This is the book closest to, I guess, Trefethen, which we will talk about today. I guess with this introduction, I would like to ask Nick to start his talk. Over to you, please, Nick.
Okay. First, I should see, can people hear me?
I can hear you, Nick.
Okay. Now, I was at Michael Overton's talk yesterday, and he saw the chat line, which seemed to be very helpful. So I should figure out where that is. Is it under attendees? I want to make sure I do as good a job as Michael. Oh, click on that. I see. Hello, everyone from Kian Far. Is that the right place? And Hazan Greenbaum said hello.
Exactly.
I'm in the right place there? And Rajendra
Yes.
Bhatia says he cannot hear too well. Behnam, can you hear me well enough?
I do.
Is it loud enough?
Yeah, I have no problem hearing, but I mean, if you can increase your voice, that would be great.
Okay, I'll do my best. And sorry, I'm a little slow starting here. I'm not used to speaking to Iran. I've now lost the photos. How do I get them back? There you are. Okay, it's very confusing. Well, let me say what an honor it is to be visiting Iran virtually. I would love to visit one day for real, but this year that doesn't happen. Hello to everybody, and thank you for organizing this conference. I am Nick Trefethen, as Behnam said, and my talk, as you can see, is about Trefethen, which is a software system, and continuous linear algebra, which is an idea. But of course, the software system implements the idea. That's our aim. And this has been a team project going back about 20 years, but the last 10 years have been the most important period. And Behnam Hashemi was one of the Trefethen team who made all this happen. I won't mention all the other names, but let me mention one. Nick Hale in South Africa wrote about half of the Trefethen code. Okay, so the way the talk will work is that on the left side of your screen will be the slides, and on the right will be MATLAB. Now, let me ask, Behnam, do you see my cursor or not?
I can see your cursor, yes.
Oh, so I must be, yesterday Overton was in document mode, and I am in screen mode, so you can see the cursor. Okay.
Yes.
Okay, so let me turn to the next page. And as Behnam just mentioned, books, but let me highlight in particular the two books that are related to Trefethen. The one he showed you is called Approximation Theory and Approximation Practice. It discusses approximation theory, but always with Trefethen demonstrations. The new edition has just come out. You notice it says 2013 and 19. So Behnam has the old edition with 1 horse on the cover, but now we have the 4 horsepower edition. Exploring ODEs, Ordinary Differential Equations, is the other Trefethen book, and this is by me and Askir Birkeson and Toby Driscoll. And this one is also a book about algorithmic or mathematics, illustrating everything in Trefethen. And this one has the special property that it's freely available. So you can legally download a PDF file of the whole book. Any of you who work with ODEs or teach ODEs, please download this book and take a look. Now, all the rest of the talk will have a fixed format. Every page will be discrete on the left and continuous on the right. And I want to talk about continuous analogs of familiar discrete things, and that's the subject of the whole talk. So to give you, first of all, the historical or software setting, MATLAB, of course, is a language and a software system based on vectors and matrices. And vectors and matrices are discrete objects. MATLAB changed the world, and it did that by encapsulating in software the algorithms that people had developed and were developing to solve linear algebra problems. So it was a mix of a good software idea with something really at the heart of applied mathematics. Now, the Trefethen idea is to overload MATLAB with continuous analogs of almost everything. Notice here I mentioned that MATLAB became object-oriented in 1996. So they introduced some objects and ways to manipulate them. That's what led to the idea of Trefethen. We figured in object-oriented programming, you can overload commands to have new meanings. So Trefethen would overload MATLAB commands to have continuous meanings. The project started in 2002 with me and my student Zachary Battles, but it wasn't very big for a while. It took 5 or 6 years before we had a team. You can see in the bottom bit of this slide a comparison of linear algebra and functional analysis. This is interesting in that philosophically, they're pretty much the same subject. Linear algebra is essentially discrete. Functional analysis is essentially continuous. It deals with functions instead of discrete vectors. And yet, if you look at these two subjects these days, they're completely different. Linear algebra is dominated by people like me and Michael Overton and Anne Greenbaum and Behnam Hashemi, the numerical people. Of course, there are theoretical linear algebraists, but they're outnumbered by the numerical ones because this technology has been so powerful. It's at the heart of computational science. So linear algebra has become an algorithmic field. Functional analysis has not, absolutely not. It's a theoretical field. I think the main reason for that is that when you start talking about continuous analogs of discrete vectors, there are a lot of challenging technical questions that come up. If you want to be fully general and fully rigorous, it's much more difficult mathematically. And of course, that's fascinating. So mathematicians like to study difficult things. The whole continuous algorithmic side of linear algebra has never been at the heart of functional analysis. And yet, for people like me, it should be. This is how you use functions as an applied mathematician. So the aim of Trefethen is to put something in that space of algorithmic functional analysis. Okay, here's the first of about 18 slides in which at the top I show you a discrete and continuous pair, the discrete object from MATLAB and the continuous object from Trefethen, and always with a picture to illustrate the idea. Now, as Michael found, it's very quiet here. So Behnam, can you confirm that you still hear me?
Yes.
Good, okay. I hope you're not the only one who can hear.
I hope so.
Here's a picture of a vector, which by default we take to be a column vector. In Trefethen, we overload that to a function, which by default we think of as a column function, and we call that a Trefethen. I'm not talking about algorithms here, I'm talking about concepts mostly, but the algorithms are all about Chebyshev series. If it's a globally smooth function, you have a single Chebyshev series. If it's piecewise smooth, you have a concatenation of Chebyshev series. If you want a reference, look at ATAP, that's approximation theory and approximation practice, or look at the Trefethen guide online. Now then, for each example, I want to type the text that you see over there on the left. And let's see this. I'll make this font is too small or too big, I trust you will let me know.
Sure.
So suppose I type x equals Trefethen of x. And that's boring, so I'll immediately make it more interesting by making a more complicated function. So I just constructed a Trefethen representing that function. And if I plot it, then you see, okay, there you see a picture of this function as represented somehow by Trefethen. It's not a symbolic object, it's a numerical object represented by a Chebyshev series. And in fact, it's a Chebyshev series with 52 terms. That's like a Fourier series, but non-periodic. If we look at the Chebyshev coefficients in absolute value, we can see that the first 20 of them are of size about 1, and then they decrease down to machine precision size 10 to the minus 15. So this is the starting point of Trefethen from 2002, realization of functions numerically in a MATLAB syntax. So any MATLAB command that you can do on a vector, you should be able to do on the function. There's an evaluation at a point, or there's the maximum of the function, or the sum of the function would be the continuous analog of a sum, which is a definite integral. I didn't mention, but by default, all functions live on the unit interval from -1 to 1. So if I plot f again, you'll see it's on the interval from -1 to 1. That was Trefethen for about 5 years, and then we introduced piecewise representations. So now I could make a new function like abs f equals the absolute value of f. And if I plot that, you see it consists of 20 or so pieces, each of which is a smooth function represented by its own polynomial. Okay, so that's our first continuous analog of linear algebra. A vector turns into a function. Now the next one is a row vector. So of course, mathematically, a row vector and a column vector are not very different, but it's very natural to interpret a row vector as a linear functional. A row vector is a discrete linear functional. The continuous analog would be a continuous linear functional, which means something that you will integrate against. There's not much to say here about algorithms. It's all the same transposed. So for example, if I say the size of f, it comes out as infinity by 1, because f is continuous in that direction and has just one column. On the other hand, if I say the size of f transpose, then Trefethen reports 1 by infinity. And in fact, if I just say f, it will tell you that f is a Trefethen column with one smooth piece. The length is 52, which means that it's represented by a Chebyshev series with 52 terms. Excuse me. If I say f prime, it's a row Trefethen, again represented by a series with 52 terms. Okay, let's move on to the next one. Once you have row functions and column functions, it's natural to take inner products of them. So in MATLAB, the syntax would just be u prime times v, and we overload that to give the appropriate result in Trefethen. An inner product, thus, is an integral. Everything we do involves an algorithm. In this case, to integrate one Chebyshev series against another is essentially what's called Clenshaw-Curtis quadrature. This was one of the operations in the very first Trefethen paper by Battles and me in DISC 2004. So let's try that. If I say, remember f, that was f. If I say f prime times f, then that will be a scalar, a single number computed by integration. And of course, the inner product of a vector with itself is the square of its two norms. So if I say norm of f squared, I get the same thing. Of course, we've overloaded other norms too. I could say norm of f infinity or norm of f1. And of course, I could take inner products of different things, like f prime against the absolute value of f, or the norm of the absolute value of f squared, or absolute value of f inner product with absolute value of f, and so on. Okay? Now, what about a matrix? So a matrix is a discrete object, and MATLAB became great because it manipulated matrices, first of all, with an elegant syntax, and second of all, with the state-of-the-art algorithms. Now, of course, an analog of a matrix is a function of two variables, continuum, a function of two variables. By default, that function lives on the unit square, -1 to 1, -1 to 1, but you can define it on any rectangle that you like. We call this a Trefethen 2, and notice how much later that came around. It was work with Alex Townsend, who's now at Cornell, in 2013. In fact, for many years, we knew we had to do things in multiple dimensions, but we delayed a while working on that until we decided what we wanted to do. And this will come up further in the talk. The basic representation is related to bivariate Chebyshev series. So that means you have Chebyshev in X and Chebyshev in Y. There's more going on that I'll talk about later. So let's take a look at that. Here I have a function f, and I'll just grab that from this side. And over here, I'll type it in. So we just called the Trefethen 2 constructor. And it takes this symbolic expression and it turns it into a numerical object, a Trefethen 2 on the unit square. That's a bivariate Chebyshev series representing this function. And of course, the idea is that you can do all sorts of things to that. For example, I could say f of 0, 0, and I should get the number 1. Or I could say f of 1, 0, and I get that. I could say plot of f. And now we're in 2 dimensions, so we're plotting a function of 2 variables. There are various ways to do that. The default looks like that. I often prefer contour plots, so if we say contour of f, then we get a picture like that. So this is a numerical representation of a bivariate object. You may wonder, if you're eagle-eyed, what's going on in the corners here? It looks like a little bit of error. Well, the corners are so close to machine precision, 10 to the -16, that the 0 level contour is hard to find. So that's only the usual kind of numerical error caused by floating point arithmetic. Here's another example. If I say sum of f, well, sum would integrate the function in one variable, giving us a one-dimensional object. If I integrate again, I get a scalar. So that's the integral over the whole domain. And I see popping up in the corner very small type from Benam. I guess people can hear me. That's good. If I had just said sum of f, then I would have had, oh, I don't know why that happened. I don't know. Oh, it was the capital. That's the reason. So there is the integral in one variable plotted as a function of the other variable. Now, a matrix is a bivariate function, but a matrix is also an object that acts on vectors, right? And in fact, that's a very interesting duality. So a matrix can be the analog of it is a function, or the analog of it is a linear operator. And this gets at something very interesting in the last 10 years of MATLAB and of applied mathematics. Matrices traditionally were both two-dimensional arrays and also mathematical objects. And the mathematical objects were the dominant idea in the early decades of mathematics. But now in the era of data science, things are beginning to move, and arrays of data are becoming more and more important. So it's almost as if the array idea has become the more dominant one. And some of the MATLAB syntax has changed to recognize that. So this notion of a matrix analogous to a linear operator would be, I think, the classic continuous analog, whereas the previous notion of a matrix analogous to a bivariate function is maybe more the data science version. Anyway, they are both implemented in Trefethen, and if we look here, I have a fairly minimal example to show you. The person who did a lot of this was Toby Driscoll at the University of Delaware, who has created many of the ideas in the Trefethen operator, differential operator. So looking at just that example, capital F is a Trefethen 2. Little x is just a Trefethen, it's a function. So I should be able to multiply capital F by little x, and I should get the continuous analog of matrix times vector, which is vector. It's operator times function equals function. So if I plot f times x, I'll get a plot of that function. That looks strange, but if you look at the vertical axis, you'll see it's 10 to the minus 18th. In other words, 0. So what's happened here is that the bivariate function f is even, and the vector x is odd. So when I apply that operator to that vector, I get 0. To break that oddness, what if we plot f applied to x squared? Now it's an even operator applied to an even function, and we get something more interesting. It's non-zero. Okay. Here's a particular kind of matrix that's of great interest for Newton iterations especially, a Jacobian matrix. I remember when I learned about Jacobian matrices and how incredibly complicated the idea seemed when you're young, and then as you get used to it, how natural it seems. It's, of course, it's the derivative for functions of more than one, with more than one component. So a Jacobian matrix is a matrix of partial derivatives. A Frechet derivative is the continuous analog if instead of having a map from vectors to vectors, you have a map from functions to functions. Trefethen implements this. The two key people are Askir Birkesson, now in London at a finance company, and Toby Driscoll. They implemented, using automatic differentiation, all kinds of derivatives, Frechet derivatives, inside Trefethen. It's really remarkable. Now, it used to be that in Trefethen, it used to be possible to type things like diff of f comma g, and you would get the Frechet derivative representing the dependence of a function f on another function g. But alas, this was Trefethen version 4, and we lost it in Trefethen version 5. So it's no longer possible for the user to get their hands on Frechet derivatives, but they're in the system all the time whenever you solve non-linear so I won't demonstrate them, but maybe in a moment with differential equations, I'll show you the effect they have. Now, what about an outer product? That's a pretty elementary idea in linear algebra, and it's pretty obvious what it should mean in functional analysis. An outer product is a rank 1 matrix that you get by multiplying a column by a row. An outer product in the continuous setting is a rank 1 function, bivariate function, that you get by multiplying a column function times a row function. And the syntax is obvious, it's what you think it should be. For example, you remember we had f, which was a column Trefethen. So the size of f was infinity by 1. The size of f prime was 1 by infinity. The size of f prime times f is an inner product, so that's 1 by 1. And the size of f times f prime is an outer product, infinity by infinity. So this is a rank 1 object. Let's do a contour plot. Just to remind you, this is what f looks like. If I now take the outer product of f with itself, I get this. Very pretty, I think. That's just a Trefethen. It's a Trefethen 2. We could evaluate that object anywhere in the unit square. Okay, moving to the next thing. Now, this is a very important analog, which half of Trefethen, in fact, springs from. What's the analog of a linear system of equations? Well, a matrix, a square matrix, is an operator. So this becomes operator times function equals function. It could be any sort of operator. It could, for example, be an integral operator. But the case that is by far the hugely interesting one is differential operators. So the main analog of a system of equations is an ordinary differential equation boundary value on an interval. The syntax is very interesting. In MATLAB, you have backslash, which means solve a system of equations. And that's a very beautiful part of MATLAB. It's one of the things that made MATLAB popular, that there was such a compact idea for invoking good algorithms to solve equations. So we decided to overload that with backslash, with a new meaning. If L is a linear or indeed nonlinear differential operator, and f is a right-hand side function, then L backslash f solves the ODE. For that to work, you need appropriate boundary conditions. So, of course, there are some details, but it's the same with matrices. Matrices start and stop on the left and the right and the top and the bottom. What's going on there? That's a kind of a boundary condition. And in the course of this work, we have very naturally thought about things. How does this discrete thing relate to the continuous world? It's a very fruitful way to learn more about both sides. This was initially conceptualized by Volkmar Bornemann, along with Toby Driscoll and me. He's a professor in Munich. Most of the implementation was then due to Driscoll and Hale, and later Birkeson. So Driscoll, Hale, and Birkeson are the three key people. And we'll also see more about some work with Jared Arndt a little later. The reference on this is Exploring ODEs, which is mostly a non-numerical book, but it has an appendix A, I think, on numerical methods. And now I want to show you differential equations in Trefethen with the graphical user interface. There's a whole syntax here that I'm not teaching you now. Some of you know it, but that would be a little too far from linear algebra. So instead of the syntax, will go straight to the graphical user interface. So I will type Cheb GUI. This was written by Birkeson, and it's a graphical user interface that is mostly for solving differential equations. And the way it does that is by invoking Trefethen commands, going back to this work by Bornemann, Driscoll, Hale, Birkeson, and myself. So for example, there's a column of a tab of demos, and I could pick one of these demos to run, and we generally start with the area equation because it's simple and has a pretty solution. So here you see the area equation written in a natural syntax. The domain is the interval from -5 to 5. Here are the boundary conditions. And we're solving a boundary value problem, ODE boundary value problem. If I press solve, then what happens is that it invokes Trefethen to discretize this by spectral methods, Chebyshev methods. And there's the solution, computed to about 10 digits of accuracy. You can see it looks like that. The Chebyshev series, as usual, decreases to close to machine precision. And of course, you can use this function as a Trefethen to work with. Suppose we wanted to change something. Suppose I want to change the coefficient from 0.01 to 0.001. Well, there we are. Or suppose I wanted to change the right-hand boundary condition from 0 to 10. Well, that wasn't very interesting, but we did it. That's a linear differential equation. But there are also nonlinear capabilities. And this is made possible by those Frechet derivatives. So for example, one of our favorite demos is called the Carrier equation, named after George Carrier. It's a nonlinear equation. You can see this variable coefficient and this nonlinear term. If we solve that, the system carries out a Newton iteration and it's completely continuous. So there's no Jacobian matrices in principle, it's all Frechet derivatives. And the iteration has converged, this is the convergence history, to that solution. And we can, if we wish, plot the Chebyshev coefficients of the solution, and there they are. Behnam, can you confirm that you can still hear me?
Yes, I can.
I could spend hours showing all these demos. Maybe I'd be happy to answer some questions now, or things people would like me to try.
So may I ask for one other demo?
Yes. Would you like me to pick?
Can you show us the KdV equation?
KdV equation, okay. That is a PDE.
Yes.
And where is it? Do we have that demo built in?
Oh, maybe that's in spin.
Yes, I guess that is in spin. I would have thought we had it here. Here's the Kuramoto-Sivashinsky equation. This is when you order groceries in England, they make substitutions. So I'm sorry, the customer wanted KdV and we gave him Kuramoto-Sivashinsky.
No problem.
If I may digress and go back to, this is what Behnam was alluding to, a command called spin, which stands for sys PDE integrator, and it will solve the KdV equation. I think it goes to time. Maybe it goes to. Where was Chip? Any other questions?
Someone has raised their hand. Do you mind if I open their microphone?
Go ahead.
Okay. We can now enable your microphone and ask.
Don't hear anyone.
Or I can just read the question.
Okay.
Blogger 4, you have microphone access if you want to ask your.
Mr. Hassani.
I don't hear anyone.
Okay. There's Mr. Karani asks, can we have the values of the solution in a point in the PDE?
Oh, absolutely. Everything here is numerical, just like MATLAB. I won't show that now. It would take a while, but yes, everything completely at your control.
Mr. Ahmad Nasab, you can enable your microphone.
Don't hear him yet.
Yes, thank you so much. And thank you for your very nice presentation. And could you please, I arrived to decision with some 5 minutes late. And could you please explain generally the main reason for actually making such a software, Trefethen, generally, and specifically why you decided to make such a software, and
Okay.
Is it clear what I asked you?
Yes, it's a good question. And I didn't say why. Of course, partly because it's an interesting idea, but from a practical point of view, I think many numerical questions are essentially continuous ones. We want to solve a differential equation. We want to work with functions all the time. Numerical analysts are trained to spend their time discretizing. I think that is not always necessary. Some of that should be routine, hidden away. Just the way we don't waste our time worrying about floating point arithmetic. That's hidden away. We pretend we have real numbers to work with, even though occasionally we have to understand the details of floating point arithmetic. Similarly, I think we should be able often to pretend we have functions to work with, although of course sometimes we have to pay attention to the discretization. So I would like to think that in 50 years this will be one of the dominant forms of computing, but I won't live.
Thank you so
Can I
much.
go on?
Thank you so much.
Okay.
So Nick, I guess there's a question by Mrs. Nagin Bagherpour.
Yeah.
Would you like to ask your question now?
I don't hear yet.
So maybe her microphone has a problem.
Is it okay now?
Yes.
Oh, sure. Thank you. Thank you very much for your nice talk, Nick. I have 3 small questions. The first one is that, but these are so small, I think know a lot of time is needed. First one is that when the chip GUI was written, because I checked on my own version and it is for 2017, and I hadn't access to this GUI.
It's much earlier than that, so there must be something wrong with your
Okay.
installation.
Sure, I will check. And then the second is that is there any error analysis on solving ODE problems using Trefethen that you show us?
We have not focused on that. Actually, Benam Hashemi knows more than I do. And also, there are some people in France, especially, interested in making these things rigorous. But I don't know anything
I see.
about it.
I see. And what about something like matrix decompositions on two-dimensional type of the chip function, or maybe rank approximation or something?
I will show you a bit of that, but we have only done a few things. There's much more. That's the future.
Okay, I see.
I think I should continue with my talk now, if that's okay.
So there are more questions. You can continue now, and then we can ask these questions at the end, or you decide.
Let's continue with the talk.
Okay. Go ahead, please.
Okay.
Yes, please.
So that was Cheb GUI. There are many more things in there we could look at, but I'll skip them. Now, what about a rectangular matrix? As we think about these things, we realize what a deep difference there is between square and rectangular. When I say square, I mean a matrix that has to be square in some sense for an operation to make sense. But of course, many operations don't require it. One generalization of a rectangular matrix is what we call a quasi-matrix, which is a finite collection of functions. So it's infinity by finite. The term quasi-matrix comes from Pete Stewart. This idea was mentioned, for example, by Carl de Boer in a paper of his, and it's also in an early chapter of the book that Benam showed you, Numerical Linear Algebra. This was one of our first aims with Trefethen to implement quasi-matrices, and let me show you the idea there. So suppose I say A equals 1x, x squared, x cubed, x fourth, for example. Then that is an object with 5 columns, so 5 functions. If I say phi of A, I get that. And I think it should be obvious how A should behave because we know how matrices behave. If I plot A times a vector, I'll type it and then we'll discuss what it means. So here I have multiplied A by a column vector with 5 entries, the first 5 coefficients of the Taylor series of e to the x. So this function will be an approximation to e to the x. Sure enough. So you can work with linear combinations of functions very conveniently in this setting. What's the size of A transpose times A? Well, it's a discrete object. Now let's persist with that point of view. What about least squares problem? Well, in a fully discrete world, you could draw that picture for a least squares problem. Rectangular matrix times short vector equals vector. The continuous analog, the simplest continuous analog, involves a quasi-matrix. So you're still looking for a discrete vector of least squares coefficients. And if we visualize that, for example, I could say with the same matrix A, I could say A backslash e to the x. And that will get me a vector of coefficients. These are now the least squares best coefficients for a degree 4 polynomial approximation to e to the x. So if I plot e to the x minus a times c, I'll see the error is pretty small. It's about 10 to the minus 3. We've also overloaded the MATLAB command polyfit, so I could also say polyfit of e to the x, comma 10. E to the x is a Trefethen, it's a function. So this p will be the polynomial that fits e to the x degree 10 in the least squares sense. So if I plot e to the x minus p, the error should now be a good deal smaller than it was for the degree 4 approximation. Sure enough, it's 10 to the minus 11. I tell you these stories, each one takes 2 minutes, but everyone actually took a year. We did a lot of thinking. There's so much fascinating algorithmics and mathematics and software involved. This one is particularly tricky. QR factorization, if you want to do Gram-Schmidt, it's obvious what's needed. But in numerical linear algebra, the right algorithm is householder, and that's not obvious. It turns out that the way you think of householder involving triangular matrices relies on the discreteness of the problem. And yet there is a continuous analog. I won't go into that, but it's there and it's very beautiful. So we can compute QR factorizations. So for example, if I say QR equals QR of A, then I get a quasi-matrix Q and a discrete matrix R. And if I plot Q, in MATLAB, when you plot a matrix, it plots the column. So this will plot 5 functions, 5 columns. Let's, for fun, take the absolute value of it. If I now plot that, what's happening? We now have 5 columns that are piecewise smooth rather than globally smooth. And the householder algorithm doesn't care. It's perfectly happy to take a QR factorization of that too. And if I plot Q, those are now the first 5 orthonormal polynomials spanning the same space as the columns of Q, as the columns of B. Continuing on, of course, there's an SVD, and here I'm showing you the quasi-matrix analog of the SVD. U is a quasi-matrix, S and V are discrete. So for example, remember we have a quasi-matrix with 5 columns. Its rank is 5. That's computed. Trefethen computes the singular values, and it counts the number of non-zero singular values. Now, what about the rank of AA, which is a quasi-matrix with 10 columns? It's 5 again, because it's rank deficient. What about the rank of the quasi-matrix with 3 columns, 1 and sine of x squared and cosine of x squared? Well, that rank is 2, because 1 and sine of x squared and cosine of x squared are linearly dependent. So we're figuring out that with linear algebra. What about the rank of x raised to the 0 colon 16? This is a matrix with 17 columns, a quasi-matrix with 17 columns. They're linearly independent, so the rank is 17. What if I say 0 to 32? They're linearly independent, the rank is 32. What if I say 64? Well, mathematically they're linearly independent, but numerically they're not. The rank is 46. Let me go on to eigenvalues. Eigenvalues of operators, of course, make perfect sense. And going back to an earlier question, This is a typical example of why we have Trefethen. When people want eigenvalues of matrices, very often these are discretizations of differential operators. That's what we really care about. So the vision of Trefethen is that the programmer should work in that continuous world. I won't show you the full syntax, but let's, as an example, illustrate the quantum states command, which is based on Trefethen eigenvalues. So here on the left, we see the first 10 eigenmodes of a Schrodinger equation with a parabolic potential function. And on the right, we have the same problem, but with a absolute value potential function. So you can see that in the Trefethen world, you don't think about the discretization. That all happens adaptively and automatically. And some remarkable things can be. The matrix exponential is another example. I like this picture of e to a matrix versus e to an operator. The syntax is a bit clumsy, and I won't show an example of that. This is a fairly new one, random matrices. As you know, random matrices have become a big subject in recent years, especially among pure mathematicians. It's of huge interest. And Trefethen has an analog for that. A random matrix, of course, has independent random entries by default. A random Trefethen has an analogous property. So let me show you. If I say f equals random fun of 0.03, and I plot that, there I have a certain smooth random function in Trefethen. If I plot the cumulative sum of f, which is the indefinite integral, then I have a smooth analog of a random walk, Brownian motion. 0.03 is a length scale. If I made that smaller, the structures would get smaller and smaller. In 2 dimensions, here's the matrix analog. If I say random fun 2 of 0.03 and plot that, then I have a function with random structure in 2 dimensions. It's hard to see that, so let's plot it in zebra mode. So there we have random functions. And again, the 0.03 is a parameter to change the length scale. We found this a very exciting thing. A smoothie, by the way, is a function at C infinity, but not analytic. Now, LU factorization. I'm really on the last 2 slides of mathematics here. In a linear algebra course, LU factorization usually comes first. In fact, my book is the only one where it doesn't. Usually this is the very first thing you do, but the continuous analog is surprisingly subtle and amazingly important in the modern world. So LU factorization is intrinsically not a square matrix idea, it's a rectangular matrix idea. It turns out that a continuous analog of that is low rank approximation, where you have a bivariate function. This is the trickiest of my images. You approximate it by a rank 1 piece, plus another rank 1 piece, plus another rank 1 piece, and so on until you capture it to, let's say, machine precision. That's LU factorization. This is the method that Trefethen uses to represent 2- and 3-dimensional functions. It was worked out by Alex Townsend, but it's related to work done by many, many people all around the world. Low rank approximation is a big deal these days. A fascinating aspect of this is that it's really Gaussian elimination, more or less. In Gaussian elimination with complete pivoting, you find the largest element of a matrix, you subtract off a rank 1 piece corresponding to that element. Then you find the largest element of the remaining matrix, subtract off another rank 1 piece, and so on. That's Gaussian elimination with complete pivoting, and it's also low rank approximation with a certain pivot selection. So Gaussian elimination is at the heart of low-rank approximation in data science. It's just amazing. And I will quickly illustrate that. Here's a Trefethen again. So if I plot f, I get that function that we've seen before. Suppose I say, what are the singular values of f? Well, you see, there are 21 of them going down to machine precision. Our function is represented by a rank 21 approximation. The rank of our bivariate function is 21. And if I plot its coefficients, there are two sets of coefficients because there's the x direction and the y direction. So two sets of coefficients and each with 21 sets of dots. I'm running a little short of time, so I'm speeding up a little bit. I won't linger on pseudospectra since we're short of time. I also won't linger on block matrices, though I'm happy to talk about them more if people want. This is work with me and Jared Arndt, now in Spain. But I do want to turn to trivariate functions, which is what Behnam Hashemi did when he was at Oxford for a few years. Of course, the idea here is some kind of analog of 3 or higher dimensional objects. In Trefethen, we only do 3. Now, this is another area where linear algebra hasn't got all the answers yet. I think classic linear algebra involving matrices is pretty well figured out at this point. But when it comes to tensors of degree 3 and higher, everything is still being figured out. This is a big, big part of data science. Well, in Trefethen, Behnam implemented the 3-dimensional analog of Trefethen 2. Of course, it's called Trefethen 3. And to do that, he does low-rank decompositions by an algorithm that he calls Slice-Tucker approximation. I won't show you the algorithm, but let's just show an analogous function in 3 dimensions. So here is a Trefethen 3. And I've just picked something that looks nice. It's a function of 3 variables. I could evaluate it at a point. I could compute its global maximum. I could compute its global integral. Let's plot it. If I plot it just like plot, as often happens, it's not very interesting. It's hard to see much in a plot. So we have various alternative ways to plot things. One of the alternatives is called slice. And with slice, you can slice through your function. We also have what's called isosurface. And with isosurface, you can look at various surfaces, various level surfaces. Now, f itself, and I'm just finishing the mathematics here, is a Trefethen 3, which consists of a lot of one-dimensional Trefethens put together in a core object of dimension 11 by 16 by 16, as it happens. And the rank of the Trefethen is the largest of those numbers. So in some sense, it's a rank 16 approximation to this 3-dimensional function. There's a lot going on here, I'm not telling. If I plot coefficients, well, for a bivariate function, we had 2 sets of coefficients. Now we will have 3 sets of coefficients. And there's the plug there. Good. So you see 3 sets of coefficients. There's columns, rows, and tubes corresponding to the 3 directives. Okay, I should finish up, so let me go to the last 2 slides. I've told you a lot of the interesting foundational things, but almost any other subject in linear algebra has continuous analogs. And you can find a number of these in the examples at the Trefethen webpage. Here are some examples. Even as simple as the great old Wilkinson matrix as a continuous analog, which is almost more important than the discrete. Tridiagonal matrices are like Sturm-Liouville operations, level repulsion, Arnoldi iteration, and van der Waals with Arnoldi. Conjugate gradients is a work in progress, but there is some very interesting work. And contour integrals is one of my favorite subjects, and so on and so on. I think this is an idea that is here to stay. And I think that's all I want to say. This final picture is a gift that Behnam gave to our family when he was here. It's absolutely glorious. And I took it down from the shelf today to photograph it. And I'm delighted how well that came out. Thank you all very much.
Thanks, Nick, for your very nice talk. And thanks for showing the Minakari. We have time maybe for 1 or 2 questions, and there is already one question that I can ask.
Yep.
So the question is, I also have the following questions. For the bivariate case, Trefethen 2, have you created the bivariate basis through the multiplication of 2 univariate Chebyshev elements in X and Y, or a mixed bivariate Chebyshev basis for the get-go?
Dear me. I'm not sure that I can answer that.
I guess the question is more or less related to whether we use tensor, the pure tensor product approach, or something different, I guess.
I guess the answer is tensor products. Multivariate polynomials have a different set, and we're always in the tensor product. Do you agree with that answer?
Yes, I do.
Good, okay.
So there is one more question by Mr. Musavi, or Professor Musavi. I'm sorry, I don't know perfectly. So the question is, would you please give some information about Trefethen architecture and their classes for developers? How the system is put together? Yeah. Is there any to-do list for the future of Trefethen?
Thank you for asking that. It's an open source system on GitHub. So it's paradoxical, open source software written in a commercial language of MATLAB. For 6 or 7 years, we had a team of 10 people working all the time on this, and we have issues and pull requests and all that. But now we no longer have such a big team. We have people maintaining the system, but it's not moving so much anymore. So yes, of course, there's a class structure, and there's about 30 classes, and it's probably more complicated than it should be. In my dream, maybe it would be rewritten from scratch, but that is not something that one person could do. You would need a very dedicated team of people. For example, this is such an interesting question, excuse me for answering at length. Many people ask, why is Trefethen in MATLAB rather than Python or Julia or whatever? Partly the answer is historical. We worked in MATLAB, and MATLAB was the original matrix vector language. But of course, Python would be interesting too. The thing is, to rewrite Trefethen is a big project. We're talking about hundreds of thousands of lines of code, many classes. It's really a major system. It's not like MATLAB in 1978. It's like MATLAB in 1996, maybe. This is a serious project. I hope I live to see a rewrite, maybe in another language, but we don't have the energy to do that on our own team.
So may I ask another question, Nick, please?
Yes, of course.
So there's a question by Professor Ken Hayami from Japan, I believe. Very happy to hear from him. So the question is there a continuous analog of the Jordan canonical form?
That's interesting. I think it would again be the Jordan canonical form with continuous functions, but I haven't thought through that. Why haven't I thought about it? But I haven't, so I'll have to get back to you. Yeah. Of course, if you look in functional analysis books, you'll find theorems related to that question. You'll find theorems related to that question. What is the spectral decomposition of an arbitrary operator? But how to connect them with Trefethen, I couldn't say off.
So I guess there is another question by Ms. Mariam, which was answered already by Mrs. Nagin Bagherpour. So I guess we can finish up, maybe, or maybe we can just wait for one more question. Is there any final questions, please? Please go ahead, Mr. or Mrs. Fazali.
I am also watching the chat line now.
So the question is how the project is funded as an open source project.
That's a very interesting question. We never had any funding. We had a little funding, but mostly we had no funding for software. It was all for research. And like so much software in an academic setting, you get funding for research and then you do software as part of that. It's very hard to get funding for software. We had a little bit from MathWorks, the MATLAB people first, but other than that, it's just been research.
Yeah, so thanks a lot for your nice talk again, Nick, and for answering the questions. I guess we have to finish up because we will be having the next talk by Professor Lee in less than 15 minutes. So we'll have a break, and so then the next talk will start.
Nick, great, thanks. It was wonderful talk. Now we have 5 minutes break. After that, Professor Lee will start his lecture. It was wonderful. Thank you.